The following explanation is provided by an excellent new teacher at our school named Greg Hurd. He's pretty awesome. So, this goes out to him. What I want you to know is that if you've got some charges over here, like let's say you start with just one charge over here, Q1, and it's a positive charge. If you want to bring another charge over here, Q2, from infinity, then you're going to be raising the energy of the situation. Of course you will. So if you've already got two charges over here, I'm going to say this is positive also. If you've already got two charges over here, like you managed to bring Q2 over, and now you've got Q1, which is greater than 0, and Q2, which is greater than 0, you're probably going to have to glue them down because they don't want to hang out. You bring Q3 over, also greater than 0, then you're going to be raising the energy of the situation further. And then, well, if you got these 3 over here and you want to bring over some charge Q4, you will again be raising the energy of the configuration. And the thing is, you know that energy divided by charge is voltage. So you'll actually also be increasing the electric potential of the area nearby these charges where they're hanging out, because as you're putting, well, you're increasing the energy of the situation and you're increasing the energy per charge, because these 3 really don't like each other. These 2 don't really like each other, but these 3 really don't like each other. So it's energy per charge. It's a ratio of the situation divided by how much of a problem you've got. And you've got a lot of charges here, but you've got an enormously high energy, so potential continues to go up as you dump more and more charges there. You can see this with a Van de Graaff generator. Hopefully you've had a chance to see one of these in class. There's oftentimes often you get a clear glass or plastic cylinder, and inside of here there'll be a belt. And the belt is going around a roller down here and a roller up here. And there's often, let's see if I can get this belt going a little bit better. The belt has to be made of an insulator, because if it's a conductor, nothing here is going to work at all. What you get is you get something down here, maybe a ground or something, and it's connected to a comb, a metal comb usually, and charges can jump off of this comb. Well, they do for some weird triboelectric reasons. You've got some kind of funny material, some fuzz down here, and electrons jump onto here, and you get a whole bunch of negative charges, and a motor is moving the belt upwards. And when the belt reaches the top, you've got a similar comb up here that's going to be grabbing the electrons, and it's on the inside of the sphere. Now, the interesting thing about the inside of the sphere, it's electrically connected to the outside of the sphere, but the inside of the sphere has to have an electric field of 0 because it's inside of a conductor. So what I'm saying is, as soon as the electrons hit this comb, they jump out to the outside of the sphere, and you get an enormous number of electrons on the outside of the Van de Graaff generator. So it is a way to generate enormously high electrical potentials. My point is, as you put more and more charges on the outside of the sphere, the potential of the sphere raises higher and higher and higher, because the energy per charge is becoming higher and higher and higher, because these charges are getting closer and closer to each other. And as they have to cram in, if you put one more electron on here, it's not just that the energy of that electron will be increased, it's that all of them will scoot over to make way, and they'll evenly distribute themselves because it's a conductor in equilibrium. So these charges on this sphere will be evenly distributed, and every single one will increase its energy. So by this equation that says it's the energy per charge, the potential is going to be increasing as you dump more and more electrons on there. And you can get potentials of 500,000 volts. I mean, depending on the size, in a classroom one, you can get 300,000 to 500,000 volts. And in a demonstration one in a museum, you might be able to get more than 1,000,000 volts. Turns out it depends just on the radius of that sphere. So I'd like to, what do I want to do? I guess I want to talk to you about 2 conducting spheres. We'll start with just one conducting sphere, but the secret is, today I'm going to teach you why electrons, well, and positive charges for that matter, like to congregate at the pointy bits. So if I have a conductor in equilibrium, you get a whole bunch of charge right there and not much charge over here. An enormously higher charge density at the pointy bits. We can define pointy bits as bits that have a very small radius of curvature. So radius of curvature is the radius of the largest sphere that will fit in a shape. And this is the radius of curvature here. You can see it's a very large sphere that would fit inside of this shape. Over here, we've got a really fantastically tiny sphere, so small that you can't see it. The radius of curvature is very small right there because it's a pointy bit. So I want to propose the idea of a charge density again, and I want to give you a sphere that has a charge density. What am I going to give you? See, I'm looking at this pointy bit, this smooth bit, and then I'm going to look at that pointy bit, and we're going to compare the two of them. I want to give you some charge Q on this thing. There it is. And the charge Q, let's make it negative so that I can draw it easily. The charge Q will be distributed evenly on this sphere. That's fine. And that means that the charge density is, what's the charge density now? The charge density, sigma, is going to be the charge divided by the surface area of that sphere. And I'm going to give you some radius r of the sphere, but it's going to be 4 times pi times r square. That's my charge density. Let me give you an r so you can see it. There. And I'll make this a capital R so it agrees. And we've got that charge density. Now, I want you to believe that the energy per charge here, the potential, is the energy per charge in this situation. It's the same as if all these electrons were concentrated exactly at the center of the sphere. You've got them all right here, right? And I want to know the potential at the same radius away from that. So there's no metal in this circumstance. I'm somehow dumping all the charges right at the center on a little speck of dust. But the potential out here at this radius, the potential here is equal to the potential there. Those potentials are equivalent whether all the charges are right at the center or whether the charges are spread around on a sphere. This gives us some really interesting results. I mean, it's really why charges congregate at the pointy bits. So I'm going to argue that the potential here is, well, the potential in this circumstance is simply Kc times the charge that's congregated right there over our radius. This is our equation we derived for potential a few days ago. And I'm going to plug in some stuff that I know. Well, we can solve this equation for Q. Q is, what's Q going to be? I guess it's just going to be sigma times 4 times pi times r squared, right? That's the total charge that's on there. And then I'm going to plug this stuff in. I get Kc times sigma times 4 times pi times r squared. And then I divide that by, what am I supposed to divide by? R. All right, so let's plug all this stuff in together. I know that the potential then on the outside of this sphere is, oh wait, what about the potential inside the sphere? I guess it's going to be all the same because remember, inside of a conductor, we find that it's always the same potential. And that's because, what's our potential has something to do with electric field. Isn't it like the integral of electric field as we go through space? So if the electric field is 0 in here, we can't change our potential, right? The potential everywhere inside of the sphere has to be the same because it's a metal and there's no electric field. So with no electric field, we get no potential change, all right? And this, of course, just cancels out the r for us. We get Kc times sigma times 4 times pi times the radius of the sphere. Now, the beautiful thing about this, then, is I can propose a similar but smaller sphere. And what I need you to know about this similar but smaller sphere is that, you probably already see it because of this argument right here, the potential of this sphere can only be the same as the potential of that sphere if the charges on this sphere with a smaller radius, what do I want to give this radius? Let's say that this radius is capital R divided by, what does it look like I'm doing? Capital R divided by 3 or something. It's a much smaller sphere. It turns out the potential of this sphere can only be the same as the potential of that sphere if there's 3 times the charge density on the surface of the sphere. And that's because in this equation, radius of my sphere appears and sigma of my sphere appears. The rest of these things, 4 pi kc, those suckers are just constants. So I need to look at this and say, if my radius decreases by 1/3, then my sigma will have to increase by a factor of 3. So this has the same potential only if it has a much greater charge density. And I think that's kind of consistent with this. This is an infinite charge density if they're all concentrated at a single point. So the potential here is equal to the potential there. The consequence of the potentials being equal. This is a very important fact. The consequence of the potentials being equal means that I can connect them with a wire and charges will not flow. A wire is metal. And every metal is an equipotential. That's something to put down in your mental toolbox. Metal is an equipotential. So when we were drawing those lines of equipotential in a really esoteric way yesterday, we were just drawing them on space. Every metal forces itself to be an equipotential. So if I connect these two spheres that have the same potential with a wire, no charge will move because they're already at the same potential. That leads me to the really natural statement then that I could draw this sphere large and this sphere small and like wrap metal around them and everything would be fine. No charges would move. There'd still be a really high density of charges over here and a really low density of charges over there. And that's why charges like the pointy bits. The positive charge. If you want to bring another charge over here, Q2, from infinity, then you're going to be raising the energy of the situation. Of course you will. So if you've already got 2 charges over here, I'm going to say this is positive also. If you've already got 2 charges over here, like you managed to bring Q2 over, and now you've got Q1, which is greater than 0, and Q2, which is greater than 0, you're probably going to have to glue them down because they like each other. So it's energy per charge. It's a ratio of the situation divided by how much of a problem you've got. And you've got a lot of charges here, but you've got an enormously high energy. So potential continues to go up as you dump more and more charges there. You can see this with a Van de Graaff generator. Hopefully you've had a chance to see one of these in class. The following explanation is provided by an excellent new teacher at our school named Greg Hurd. He's pretty awesome. So, this goes out to him. What I want you to know is that if you've got some charges over here, like let's say you start with just 1 charge over here, Q1, and its charge is voltage. So you'll actually also be increasing the electric potential of the area nearby these charges where they're hanging out, because as you're putting, well, you're increasing the energy of the situation and you're increasing the energy per charge because these 3 really don't like each other. These 2 don't really like each other, but these 3 really don't. They don't want to hang out. You bring Q3 over, also greater than 0, then you're going to be raising the energy of the situation further. And then, well, if you got these 3 over here and you want to bring over some charge Q4, you will again be raising the energy of the configuration. And the thing is, you know that energy divided by charge